Okay, hi everyone. In this video, we're going to go ahead and talk about the different types of reactions. And it's really helpful to classify reactions according to different definitions because sometimes it makes it easier to balance those reactions or to understand what's going on. So let's go ahead and get started. Okay, so the first type of reaction is a decomposition reaction. So in this type of reaction, we have one starting material which is going to break down into two or more products. So if we look at this general form picture you have below, the A is bonded to the B, and then after the reaction, they are separate into two different components. So that is a decomposition reaction. So for some different examples, the first one we have is sodium chloride, which is table salt. So we can actually break table salt into its different ions. We can get sodium ions and chlorine. The next one is hydrogen peroxide. Okay, so hydrogen peroxide can decompose into water, H2O, and oxygen gas, or O2. That's why it's so helpful for cleaning. That oxygen really is a great cleaning agent. And then the third one is sodium bicarbonate. Okay, so this is baking soda. So with baking soda, when it's exposed to heat, like in your oven, it breaks down into sodium carbonate, water, and carbon dioxide. And that carbon dioxide is what helps to give those baked goods that lift to make them light and airy and fluffy instead of dense. So that's how sodium bicarbonate or baking soda helps out with baking. The next thing we have is a synthesis reaction, which is the exact opposite of a decomposition reaction. So we take two or more starting materials and we combine them to get one single product. Okay, so in this case, the A and the B are separate to start, and then they bond together to form one product. So some examples of this: iron plus sulfur gives us iron sulfide. The exact opposite of that sodium chloride example from earlier, if we take sodium and chlorine, we can combine them together to get sodium chloride. And then the last one, SO3, so sulfur trioxide, plus water can give us sulfuric acid. Okay, the next one we have is a single replacement reaction. In single replacement reactions, which are also known as single displacement reactions, we take a single element by itself and it's going to trade the place of another element in a compound. So if we look at the general form, we see that A and B are bonded together and C is by itself. Well, after that process, the B and the C are trading places. So now the A is bonded to the C and the B is all by itself. Okay, so one tip for identifying single replacement reactions is to look for a single element by itself, one that is not bonded to anything else on both the reactant and the product side of the reaction. And make sure it's on both sides. That's how we know it's single replacement. If it's only on one side of the reaction, that's either going to be a synthesis reaction or a decomposition reaction. And an analogy for single replacement reactions is when someone cuts in at a dance. So you have two people dancing together, and then someone else comes up, they trade places with someone who is dancing, and now there's a new couple that's formed, and someone else is by themselves. So some examples of this, we have zinc by itself, and when it mixes with copper chloride, the zinc and the copper are going to trade places, okay? But again, the zinc is by itself in the beginning, the copper is by itself in the end. The next one, we have silver nitrate and copper. When they combine, the copper and the silver trade places. And then finally, when we have zinc and hydrochloric acid, the zinc and the hydrogen swap places. Okay, so every single time we have an element by itself on the reactant and the product side, but it's something different. Okay, the next type of reaction we have are double replacement reactions, also known as double displacement reactions. And it's very similar to single replacement, except for we have two things trading places, okay, not just a single one. So if we look at the general form, A and B are bonded together initially, and C and D are bonded together. But they're going to go ahead and trade who they are bonded with. So in the end, A is bonded with C, and B is bonded with D. We're going to do a lot more examples of these because they're really common for precipitation reactions. Okay, so one thing I want to point out for double replacement reactions, the cations are going to trade places with another cation. Or you think about the anions trading places. But they have to keep their same identity. A cation will not become an anion. We always need those opposites attracting one another. So an analogy for this is square dancing, okay? So everyone has a partner, and then at some point in time, the caller says, everyone trade places. and then you get a new partner, but no one is left out. Everyone still has a partner in square dancing. Okay, so some examples of this. We have sodium sulfide and hydrochloric acid for the first one. They trade places, so now the sodium is with the chlorine and the hydrogen is with the sulfur. And again, cations are still cations and anions are still anions, and we have the opposites bonded with each other. Okay, so if it comes at the beginning, it still needs to come at the beginning. If it comes at the end, it still needs to come at the end. The next one, lithium sulfate and barium chloride, those two react to give us lithium chloride and barium sulfate. And then finally, sodium hydroxide and hydrochloric acid react to give us water, H2O, and NaCl. Now, water can be a little bit tricky because it doesn't really look like it's having that beginning and the ending, but we can also rewrite it as HOH, okay? So we're taking the OH for the sodium hydroxide and the H from the hydrochloric acid, and that gives us the water. So I promise it is a type of double replacement reaction. And in fact, it is a special type of a double replacement reaction known as an acid-base reaction. Okay, so acids generally contain hydrogen atoms and bases generally contain the hydroxide ion. And when those two things combine, we get water, H2O, and some other ionic compound. So there's two different ways we can kind of think about it. Like I said, that first one there shows that HOH, where the H comes from the acid, the OH comes from the base to give us that water. Or if we just stick it all together, kind of simplify how things are written out, we can think about that bottom example there. So some different examples, that sodium hydroxide hydrochloric acid one I talked about earlier, you can either think about it as a double replacement reaction or an acid base. Either one is acceptable, although acid base is a little more descriptive, so that's the better choice. And then the next one, we have sulfuric acid plus potassium hydroxide. They react to give us potassium sulfate. Okay, so the K and the SO4 combine together, and then we get water. Okay, the final type of reaction we can have is a combustion reaction. So for combustion reactions, we have a hydrocarbon. And this is something that contains both hydrogen and carbon. And it can be different amounts of them, but it has to have those two elements. And then this is going to react with oxygen, O2. And the two products you always get from a combustion reaction are carbon dioxide and water. Now, you're probably pretty comfortable with carbon dioxide being produced from burning things. Well, we also get water, which seems a little counterintuitive. But I want you to keep in mind the amount of water that's produced in this case is very, very small. Okay, just be a little bit of a condensation, really. It's not a whole bucket full of water. This is why it's different and doesn't put out the flames. If we take a whole bucket of water and pour it onto something that is burning or combusting, what we do is we actually smother the oxygen. We prevent the O2 from going in. So that's why we are able to put out flames using water. Even though it's a product, it all works out. So the one thing I want to really remind you about combustion reactions, you want to be careful with balancing them. Always balance the carbon first, the hydrogen second, and then the oxygen last, okay? That makes your life much easier. And sometimes when you get to the oxygen, you're going to find that it's not working out. You have a weird fraction thing going on with your coefficients, which we're not allowed to do. So you're going to multiply everything by 2, and then it will all work out. So some examples of this, we have methane, which is CH4, plus oxygen gives us carbon dioxide and water. And then the next one, we have C2H6 plus oxygen gives us, again, carbon dioxide and water. You always get the same two products for combustion reactions. So I hope this helps. If you have any questions, please let me know. Have a great day, everyone. Bye.